Yo, yo, what's up? All right. So I'm kicking off a series that is really going to be focused around a product that I'm going to build here. And I'm going to build it sort of through this entire series. And it involves a lot of stuff that I've never really done, but always wanted to do. So it's an embedded system. Um, it's a musical instrument. Well, sort of. At some point, I'll get to the actual product and make a whole video over what it is and kind of the idea behind it. Um, but there's some embedded work in there, and then there's also a desktop application that'll have to go with it. That'll kind of be the core bit of how the product works. And what I'm going to be using Juice. So if you're not aware of what that is, it's essentially a I don't know. Would you call it a framework or would you call it development framework? That's what they call it. But essentially, what it does is allows you to build audio plugins for all of the major um, uh, digital audio workstation softwares that are out there. It's got uh, a lot of really cool libraries built around it, and some of that is it's got its own UI framework built in. I'm not going to dive into it just today, but it's got all the core libraries for any sort of digital signal processing that you're going to need. It's got MIDI library already built in, which I'll definitely need to take advantage of. Now, I'm not making a plugin per se. I'm making a standalone application outside of a digital audio workstation or a DAW, but it will be plug-inable at some point. So that's kind of the reason I chose Juice. I'm not a C++ developer by trade. I've used it on and off, but never super extensively. Um, and so part of the beginning of this whole journey is going to be focusing on learning um, C, C++, really cutting my teeth on um, memory management and those types of things, and really try to get my performance chops down. It'll be a learning and going as I go along, but I've had a few things that I've wanted to build over time. A real time operating system has been one of those things that's kind of always been in the back of my mind. Um, and so I think what I'm going to start with is looking at building a small hash table, um, and just sort of understanding the mechanics behind that. And then from there, start looking at different types of allocators, like a linear or a arena allocator, or some other type of allocators. I think those will probably be the best for leveraging in an embedded system, but maybe not. I mean, I may learn that as I go as well. And then what else? Task management, all that sort of stuff. So, and the reason why is, this tool, this instrument. It's not really an instrument. It's not really a tool. It's kind of somewhere in the middle. But I want to be able to have like custom settings and things to be able to store in there, and so being able to store those and access them quickly out of some sort of hash table where I can cache that information seems like it might be relevant. So, and I could be completely off base on that as well. We'll figure it out as we go. But um, nonetheless, I figure I started looking at. So I was reading this how to implement a hash table in C, and and then later on came across this paper. Um, and I thought, what, this would be a good place to start. So what I'm going to do is I started reading through this and uh, Ben Hoyt has kind of defined the high level. I mean, he's totally implemented this, but I don't want to. I don't want to copy it. I want to try and give it a swing myself. So, um, what I want to do is sort of give a breakdown of the approach, what the hash function is that we're going to use. I'm just going to leverage the same 64-bit um, FNV hash function here. So I found a Wikipedia page on that that's got the actual algorithm for this. This one more specifically since it's the 1A. And so I think what we'll do is we'll start like let's play around with implementing this hash algorithm in C. Um, and then see if we can stand up like a small little hash table, and we'll start from there. I think that'll be the best place to start. And then once I get that done, I can go and because I have these references, I can look at the different implementation down here. I'll probably follow somewhat of this API design, just so it's somewhere in the same lines, and then refine it over time. Eventually, this will have to be updated to work in an embedded environment, but I'm going to start just learning the mechanics underneath all this. So with that said, let's go ahead and get started here. So I think the first thing I want to do is I like to get a visual understanding of what it is that I'm trying to build here. And so from the perspective of a hash table, I think, ultimately the process is you have some sort of backing array, right, that'll hold the values that you're trying to store. And the goal here is, to run at constant time. I just made that worse. But the goal here is to run at a constant time. And there's a couple things I think I'll have to consider along the way here, like collision detection and all that stuff. But the core of the algorithm is cool. Nailed that first try. So I was trying to get an array with size 8. So essentially what we're going to have is, you have some sort of key value pair, right? So you have a key, and then you have some sort of value, we'll say 100. And what I want to do is I want to be able to take this key and do a constant time lookup of this value, right? And this value will be stored in this table somewhere, or this array somewhere, and the hash function is the thing that's going to allow us to grab that at constant time, because we won't have to search this. And so the way that works is essentially you have, this will be our, this is like a black box sort of thing, right? This is our hashing algorithm. And this is, you have this hash function here, right? And so what we want to do is we want to say, hey, we want to take our key and we pass that value into the hash function. And essentially what the hash function will do is return out a deterministic value. So let's say this key, for brevity's sake, after it comes out of the hash function, this gets hashed into the value 21. Okay, so what does this mean, right? So this spits out a value of 21, but obviously this array is only 8 elements big. So what do we do with this? Well, there's kind of two approaches. They ultimately do the same thing, but what you can do is you can use the modulus operator and grab the remainder of this. So you can do 21 modulo 8, and this will give you some sort of index value within this array, right? So let's just say 21 modulo 8. I don't know what that's going to return. Let's say this. Actually, we could figure it out. Let's figure it out. So 21 in binary is let's just cheat here, and I've already got my calculator. So cool. So 0, 0, 0, 1, 0, 1, 0, 1. Okay, so we'll say 21 equals a binary of 0, 0, 0, 1, 0, 1, 0, 1, right? And essentially, what the modulo operator is the same as saying, uh, it's essentially, how do I explain this? It's like, so 8 uh, at base 2, so we can get this into binary, would be what, 2 to the third. And so a modulo, essentially, what you can do is you can take whatever this is and grab the bits off of the value you're trying to modulo against, right? So we could basically take off these last 3 bits here, and that would give us 1, 4, so that would give us 5, right? And so that's essentially what the modulo does. This gets the n bits, off the end of the binary value, right? Is what you get. Another way to do it is you can AND it with your value minus 1, or the nth power minus 1. So in that case, it would be 7, and 7 in binary is all ones at the end, right? So it would be B 0, 0, 0, 0, 0, 1, 1, 1. And if we ANDed these two together, what we would get is 0, 0, 0. That would convert to 0 since it's not an AND. That's a 0. So what we would get is essentially just these last 3 bits again. So you get 0, 0, 0, 0, 0. These would be ANDed, so you'd get a 1. These would not AND, so you'd get a 0. These would AND, so you'd get a 1. And we get the same value, right? So this still is 5 as well. I hope that's probably as clear as mud, but essentially what the modulo or the ANDing against the value minus 1 allows us to constrain that to how many elements we have, or what the capacity of the backing array is. And so that's what the algorithm will do. So in this case, we get a value of 5. And so what we'll do is we'll take this value of 100 and we'll stick it in the 5th index of this. So we say 0, 1, 2, 3, 4, 5. And then right here, we place the value of 100. Okay. Now let me erase some of this real quick, clean this up, give myself a little room. Okay, so now that we have an idea of what the hash function is, the benefit of this is that it's deterministic, right? So now every time that I provide key, it's going to spit out a 21 modulo on the 8 or whatever our capacity is, and it's going to always produce the same index. So now instead of having to do a search for the value, I can just go out and grab the value. So that's the mechanics of a hash table underneath the hood. Now, there's the problem with that is, what if I have a key called val or something, and I plug that in, and it also results in a 21, same capacity, so we still get the value 5, right? And let's say for this one, we had val, and let's say the value here is 75. So we want to stick 75 in index 5. Well, the problem is if we go and we look at our array, right, this is already occupied with data. So if we try to do that, it's going to overwrite this value. And then later on, if we try to retrieve key, we pass key to the hash function, we get index 5, we go grab 5. Well, now it's been overwritten with 75, right? And so now this is that collision issue that we have to figure out. So one of the simplest approach is, let me back this off real quick. It's called linear probing, which is basically, okay, I look at this value, it's got a value in it, so I'm just going to move over to the next one. Oh, this thing is empty. I'll put my 75 in here. And so now I haven't overwritten this, and this is being stored in a new array. Well, now we have another issue, and this is all of this makes sense to me. One of the things I'm going to have to figure out, because I haven't gone down this far down the rabbit hole, is if I still pass 70, or if I still pass val in here, I'm still only going to get 5 out. So I have to have some mechanism to know that val hashed is equal to 5, but we stored it in 6, right? So there's still a miss here that I haven't quite figured out. We will figure that out as we go. Okay. Cool. So with that, I think what I want to do first, at least for the remainder of this video, is let's jump in and start building out. I want to go ahead and implement our hash functions and kind of test this this underlying logic that I have. So back here, in determining the actual, where's it at? And so in determining the actual hash algorithm, I don't exactly know why this one was picked, but I'm gonna just leave it at that, and I'll probably at some point, especially whenever I move it to a a real-time system, an embedded system, I'll have to really consider this because I have to understand how many clock cycles is this going to take every time I need to go grab a value, because part of this musical instrument is extremely precise metronomic timing, and so I have to start thinking about these things when we get to that lower level. Some of this stuff may have to be converted into assembly so that I can really look at the clock cycles. But for now, we're going to start with this one just because it's what, for learning purposes, it's what this article is using. So I'm just gonna go with it. Cool. And I hash table and see if you look that up. Ben Hoyt, I definitely think it's worth a read. We'll probably kind of read through this together as I get further and further past this point, especially once we start comparing implementation. Okay, so with that, let's start with implementing this algorithm. That's what I want to do first, is actually implement this. So let's get a terminal pulled up here. Okay, so that's not what I want. Actually, let's go into learning C, and we'll take a hash table, and let's just start with main. Okay. Whoops. Oh my gosh. Let's try this one more time, and like it's not my first time doing it. Okay. All right. So let's define our main here, and then let's start with, what do I need? I'm going to need to include the standard library, and then also for now, let's also, because I'm going to try and print some stuff out, let's include standard IO. Okay, so perfect. Let's start. Let me come back here real quick and look at this. So I think what I'll do is in this one, he mentions that he's going to start with an array of 16 elements. So I'm going to kind of follow along with that, and we'll keep this as our initial capacity of 16, and I think we're going to need a hash function here. I'm not sure what we're going to need to pass in just yet, but let's see. Let's look at the algorithm real quick. Okay, so the algorithm is, first we set the hash to an FNV offset basis. I don't know what that is. So, okay, I may have to figure that out. Oh, okay, right here. Okay, we'll look at that in a sec. And then the algorithm is essentially for every byte of data, we're going to update the hash with an exclusive OR operation of that byte. So we take our hash, we XOR it, and then another thing, FNV prime. Okay, it's over here too. And then we multiply it by the FNV prime. Okay. Okay, so then what we're going to need then is an array of data. So this is going to be our key that comes in. And we don't want to change. So let's just make it a const. Okay, and then so the hash is also needs to be a size t, because we are going to have to multiply. And then this equals what? I'll set it to 0 for now. So this needs to equal, I wonder if that is a constant value. Let's see. Offset basis. There are several different FNV offset bases for various bit lengths. These offset bases are computed by computing the FNV-0 from the following 32 octets when expressed in ASCII. This is one of null signature lines. This is the only current practical use for the FNV-0. FNV-0. Oh, so this is deprecated, but we can use this to determine the offset basis? Except for the computing of the FNV offset basis. Okay. Okay. Okay, so this, alright, so this, so we can make this a function, and this will return the offset basis for us. Okay, which, what is this? It's still, I still need this prime. So it starts at 0, and then hashes, multiplies by the prime, and then XORs. Okay. What is the prime? A prime number is determined as follows. For the given integer s such that s is greater than 4 and less than 11, let n equal 2 to the s and t equal, I don't know what the hell that is. I'm not a computer scientist or a mathematician. Then the n-bit FNV prime is the smallest prime number p that is in the form of 256 to the t plus 2 to the 8 plus b. Oh, look. You know, I wonder if I could just use 64-bit, right? Because that's what we're making. And we could just store these as, okay, let's try that real quick. Okay, so let's just define a couple constants here. FNV offset basis. What the hell? Okay, what was that value? Oops, wrong way, wrong way. Okay. store it in hex. Why? Because I just want to. What are you doing? What the hell are you doing? Okay, and then define the FNV prime. Yeah. Okay. 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 FNV. Like this. Okay. All right. So now let's go back to the algorithm. What does the algorithm look like now? So I start with the FNV basis, the offset. And I say FNV offset basis, like this. And then, let me include, because I'm going to need to get the length of this value. Okay, and then we're going to return the hash at the end. Okay, so for, hey, what the hell? Yeah, I mean, I can do that and then not include this. I kind of like the stir length, but whatever. Copilot disable like this. Okay. Yeah. Don't want that. I don't want that, okay? Okay, I'm trying to learn, man. You're trying to take away my learnings. Okay. So cool. Let's see. Let's do this. Let's print that out real quick and say, yeah, because we have our capacity. Let's try this. So let's just try a few, let's do a few keys here. We'll call this, we'll say key 1 equals key. And then what do we do? Let's do the other one as key 2. I think we said it was val. Cool. And then so we have a size t of res1 equals, let's call this a hash with key 1 in it. We'll say 2 with key 2. Okay, and then let's print these out. Key hash is what? Size t, is this LU, I believe. Spend some time, or is it UL? Unsigned long? I think that's it. Whatever. We'll figure it out, man. So let's do key1 and res1. And then we'll do this key 2 and key res2. Okay. Let's see. Okay, so we say what? GCC dash O. Let's call it main. And then let's just run the main. Oh no! It did print, but I got some warnings. Okay. Oh, LU. Man, I was right the first time. Okay. Let's try it again. Boom! Look at that. Okay. Okay, so now let's do the is it a size T? Yeah, we'll just leave it so I don't have to do any casting. We'll say index 1 equals res1 the init cap. We'll call this index 2. Just 2 key Okay. IDX1, IDX2 like this. Let's run that. Oh, see, and they both turn out with interesting, right? It wasn't 5, but it's interesting they actually both came out with the same index. Okay, that's cool. Uh, am I am I a genius? Did I predict? Did I predict that those two keys would actually collide? What if I change it to this? Okay, now we have a different one. So that's the key. Interesting. So we've got the hashing algorithm in place, so that's cool. That was actually relatively easy. I thought that was going to be a bit more of a pain in the ass. But hey, cool. All right, so next, what do we want to do? What do we want to do? I've got 10 more minutes here. I think what I'll do actually, you know what? Let's do this. So let's mock out what I want to do next is so I want to let's clean this up a little bit because at some point I'm going to have more functions in here and I don't want to have to worry about the order of them up there, so I'll start stubbing stuff out here. Okay, so I'll also eventually probably break this out. Maybe not. I don't know. You know, this is more for learning. I'll just keep it in one file. Okay, so let's see. What am I? Let's define the structures, right? So let's do a let's call this a hash table. Is that how you? I think it's been a while. I think that's how you do a type definition. Okay, and so we have to have some backing array to hold these values. The other thing is, so what we could do is call this like what, an element. And then in here, we can actually keep the string key, and then I think probably a void star of the value, because yeah, that way I can stick whatever in there and then we can cast it. Okay. Okay. So, and then in the table, what I can do here is, yes, I can have an array. How do I do this? If I want an array of elements with a init cap like this. Actually, no. What I'll do is I'll just leave it here, and then I'll allocate the memory. So we'll have a kind of a create and delete, or an init and delete or something. Okay, and what we'll do is we'll store the. Yeah, I'm thinking we'll have a capacity. And then we'll have a count. Because one of the things that I want to do, you know, we have to track, we'll initialize it to the initial capacity. And then we can access that. But at some point I may want it to grow. So it'll initialize with a predefined. But let's say, you know, it's 16 elements. At some point we've got 12 elements stored in there. We may want to grow that, right, and copy that memory into a, you know, maybe a 32 size array and sort of double it every time it gets to some threshold of being full, For now, I'm not going to worry about it. For now, if it's full, I'm just going to return null and be like, hey, the table's full. You can't add anything else to it. But I do want to look at growing it just to understand that mechanism. Okay, so I think let's start with this. I think cap, and I'll have a hash table pointer, and we'll call this init table, I guess. Do I need to provide anything? I think that could just be void. I may. No, that'll be fine. And then we'll need to be able to destroy this table too. I want to say demolish table. Yeah, and then we'll take a hash table in, so I know what to destroy. And here we'll go in and free all that memory. Okay, cool. So we'll start. All right, so this is going to be what we come up with next. If you're watching this, I would encourage you to go try to implement these two. One thing that I will say in the initialized table, now that I'm thinking of it, so because we're going to be, where's my drawing pad at? Here. So because we're going to be, let me redraw this real quick. Last thing. So because we're going to be doing linear probing, what we want to do is all these values. So what we're going to store in here is going to be, think of it as a key value, right? It's going to actually hold the reference to our element, right? I think this is how I'm going to approach this. So the element, right? Elements. And this will be the elements array. And so, we've got 1, 2, 3, 4, 5, 6, 7, 8. No. Sometimes you just do stuff that you're like, what are you doing? I just need 7. Okay. And so these will all hold references to the elements. So one thing, though, is what we're going to have to consider is the first thing before we can insert, we have to check. So in the initialize, we want to make sure that all these are initialized to an empty value, not just random values, random addresses. So because what I want to be able to do is I want to say like, else, and I want to be able to look into, whatever the ith index is, and then say, peek in there and say, hey, is the key in here? Is that null? I think this is how I want to approach it. And then if it's null, then we can insert. If not, then we have to linear probe this thing, I think is how I'm going to approach this. So with that thought, the reason I bring this up is in the initialization of the elements, I think what we're going to have to do is use a calloc, malloc, calloc, of, our cap times her, I guess really it would be the other way, but it'll be, 16, ultimately 16 slots big enough to hold an element that get initialized to a zero state. I think that's how calloc works. I may read on that, but this is kind of what popped in my mind just now. I know it works with, like, if I have an array of ints, it'll set all of them to 0. I'm not exactly sure how it works with structures, but we'll go figure it out. Maybe it sets it to an empty I don't know. I'll figure it out. So anyway, that's what we'll do next. Is I'll actually come back and we'll implement the methods for creating and destroying the table, and then I think what I want to do is I want to test that. Let's actually add that too, because I want to be able to print table, and so I want to be able to look at this as we go and just see what values are getting stored in the table. And we already know that. I'll actually change this back so I don't forget. We already know that this is going to collide, right? This will collide with key at index 12. And so what's cool about that is we can already test some collisions and see how we already know a value that will collide, and we can start looking at the linear probing implementation. Cool. So, all right, let's stop there, and I will see you guys next time.